Thomas A. Grossman and Vijay Mehrotra introduce a comprehensive taxonomy for analytical spreadsheet models, incorporating both use case and engineering resources devoted to development. This taxonomy expands upon a previous three-type classification, identifying 9 distinct types of spreadsheet models that encompass various analytical spreadsheet models found in the literature. The authors differentiate between an analytical solution and an industrial quality analytical spreadsheet model, providing definitions and relating them to existing literature. They hypothesize how these types might arise and highlight the taxonomy's benefits, including identifying where spreadsheet development guidelines are most useful, providing a lens for viewing spreadsheet errors and risk, and offering a structure for understanding how spreadsheets change over time. The importance of spreadsheets in business is well established, but they can also be a source of risk and costly errors. Researchers and practitioners have been working on articulating standards and practices to reduce risk and error, and increase productivity and effectiveness. However, professional practice recommendations must be limited to a well-defined domain or class of spreadsheets, necessitating a taxonomy. Building upon their previous work, Grossman, Mehrotra, and Sander, 2011, which provides a taxonomy based on how the spreadsheet is used, the authors consider the domain of analytical spreadsheet models. The analytical spreadsheet model domain, illustrated in Figure 1, serves as a foundation for the proposed taxonomy. This taxonomy opens the door to numerous research questions, including refinements to itself, and provides a framework for understanding the complexities of spreadsheet development and use. The domain of analytical spreadsheet models is distinct from spreadsheet models in general and spreadsheets in general. According to Grossman, Mehrotra, and Sander, an analytical spreadsheet model is a spreadsheet computer program that implements a mathematical model, serves as an organizational asset, and is employed in an important context. They emphasize that analytical spreadsheet models are primarily about the business logic embedded in the model, excluding data-driven models with large datasets and few cell formulas. The authors differentiate among 3 types of analytical spreadsheet models: personal productivity tools, analytical spreadsheet models, and spreadsheet applications, with increasing recommended engineering effort for each type. This paper extends and refines this taxonomy into a richer 9-element model, providing insight into the creation, development, and evolution of analytical spreadsheet models over time. The proposed taxonomy identifies 9 types of analytical spreadsheet models, including the newly distinguished analytical solution and industrial quality analytical spreadsheet model. Each type is characterized by its use case, development criteria, and appearance in literature, allowing for a deeper understanding of under- and over-engineered spreadsheets and their associated costs and risks. The authors argue that spreadsheet development guidelines should vary depending on the business context, and this taxonomy provides a framework to understand existing development recommendations and identify areas where new guidelines or risk management measures can be developed. This paper refines the Grossman, Mehrotra, and Sander, GMS, 3-type taxonomy for analytical spreadsheet models, aiming to clarify and extend it. The GMS taxonomy considers 3 types of spreadsheet models: personal productivity tool, analytical spreadsheet model, and spreadsheet application. To avoid confusion, the term analytical spreadsheet model is used only to describe the domain of spreadsheet models under consideration. The paper also relaxes a key assumption in GMS, which conflates the level of spreadsheet engineering investment with the type of analytical spreadsheet model. Instead, it proposes a 2-dimensional taxonomy that considers the intersection of 3 use cases and 3 engineering resource levels, leading to a new taxonomy featuring 9 types of analytical spreadsheet models. This refined taxonomy is crucial for understanding the diverse nature of spreadsheet models and their development processes. The authors expand on the GMS taxonomy by illustrating different investment levels and the assumption of alignment between spreadsheet engineering investment and model type. Figure 3 displays this extension, featuring 3 spreadsheet model types from Figure 2 and the GMS alignment between spreadsheet engineering investment and type of analytical spreadsheet model. To refine the axes of Figure 3, the authors introduce new terminology. The horizontal axis is renamed to use case, defined as a specific situation in which a product or service could potentially be used, and is divided into 3 categories: unique analysis, business process embedded, and spreadsheet application. The vertical axis is renamed to engineering resources, encompassing resources such as time, managerial attention, and expense, and is categorized into 3 levels: low, medium, and high. This refinement yields the use case engineering resources taxonomy, presented in Figure 4, which enables consideration of the interaction between engineering resources deployed to build an analytical spreadsheet model and the situation in which that model will be used. The taxonomy highlights 9 combinations of engineering resources and use cases. The authors then revisit and refine the 3 types of spreadsheets from GMS, renaming them and placing them into Figure 5, which indicates alignment between engineering resources and use case. The names of the boxes are adjusted to reflect this alignment, demonstrating the intersection of engineering resources and use cases in analytical spreadsheet models. The Personal Productivity Spreadsheet (PPS) model is introduced, distinguishing it from a personal productivity tool. The PPS model is further classified into 3 types: the Industrial Quality Analytical Spreadsheet Model (IQASM), which receives significant investment, and the Planned Application, which involves appropriate engineering resources in its development. The Use Case Engineering Resources Taxonomy, illustrated in Figure 5, highlights the importance of aligning use cases with engineering resources. However, the authors argue that a direct alignment between the two is not always necessary. Figure 6 presents a simplistic representation of the taxonomy, assuming that engineering resources should be aligned with use cases, resulting in waste when resources exceed requirements and danger when resources fall short. The authors contend that this assumption is not always valid, and that it can be suitable for a spreadsheet to exist in a misaligned cell. The authors explore the use case dimension of the taxonomy, identifying 3 primary use cases: unique analysis, business process enabled, and spreadsheet application. These use cases are not exhaustive, but they aim to capture the bulk of real-world spreadsheet models. The authors acknowledge that their proposed use cases may not cover every possible circumstance, but they hope to provide a useful framework for understanding spreadsheet models. Spreadsheets are utilized in various ways, categorized into 3 distinct use cases: unique analysis, business process enabled, and spreadsheet application. The unique analysis use case involves building a spreadsheet model for a single calculation or analysis with limited scope or time, often not shared beyond a tight team, such as financial models for specific projects or personal interest rate spreadsheets. In contrast, the business process-enabled use case involves spreadsheets used regularly within an established business process, typically transferred to the new business process owner upon user change, which can lead to accidental legacy systems. The spreadsheet application use case involves developer-created spreadsheets distributed to multiple users, often with unspecified intentionality. Each use case is characterized by aspects such as intended frequency of use, accessibility, number of users, and reliability of user behavior, as detailed in Table 1. Notably, a given spreadsheet can fit into any of the 3 use cases based on the business situation, rather than the spreadsheet artifact itself. However, the risk of misuse or inadvertent damage is not explicitly included in Table 1, as it is influenced by the engineering resources devoted to spreadsheet development. These use case aspects will be crucial when combined with engineering resource levels, as discussed in Section 5. The paper discusses the development of a taxonomy for spreadsheet models, focusing on 2 primary dimensions: use case and engineering resources. The use case dimension is categorized into 3 levels: personal, departmental, and enterprise, each with distinct characteristics such as complexity, distribution, and the level of support required. The engineering resources dimension also comprises 3 levels: low, medium, and high, which vary in terms of development standards, cost, effort, and relative time. For instance, the low engineering resources level involves minimal expense and effort, while the high engineering resources level entails significant investment in both time and cost, along with sophisticated user interfaces and rigorous development standards. Combining these 2 dimensions results in a 3x3 matrix, resulting in 9 types of spreadsheet models. 4 of these cells are shaded, indicating they are commonly seen in the literature and widely accepted as desirable. The unshaded cells represent less desirable situations or those less explored in the literature, but still relevant in real-world scenarios. This taxonomy aims to provide a framework for understanding and categorizing spreadsheet models based on their intended use and the resources invested in their development. The development of a taxonomy for spreadsheet development is crucial, particularly focusing on the business process-enabled use case. A prime example is the Industrial Quality Analytical Spreadsheet Model, IQASM, which excels in efficient analysis, readability, transferability, accuracy, reusability, and modifiability. This model is classified as a tool by Olofsson and Fry, 2008, and its handover from developer to user has been discussed by Reed and Batson, 1999. The taxonomy provides a framework for understanding the evolution of spreadsheets over time, paving the way for future research into development guidelines, risk assessment, and risk management. The authors introduce the concept of a gold-plated spreadsheet model, combining a business process-enabled use case with high engineering resources. This scenario may be desirable in situations where future users are not carefully selected or handoffs might not be sustainable, but it can also represent a waste of time and money spent on over-engineering unnecessary features. In contrast, the field-expedient spreadsheet model is characterized by a business process-enabled use case with low engineering resources, resulting in a spreadsheet that is not sufficiently developed to make it an industrial quality analytical spreadsheet model, IQASM. The authors also discuss the unique analysis use case, involving building a spreadsheet model for a single calculation or analysis. This includes the personal productivity spreadsheet model, characterized by low engineering resources and intended for one-time use, and the analytical solution spreadsheet model, defined by medium engineering resources. The paper explores various types of spreadsheet models, emphasizing their distinct use cases and the level of engineering resources invested in them. One such model is the analytical solution type, which is crucial in certain business contexts due to its efficiency, accuracy, and reusability. Examples include Olofsson and Fry's practice at Hewlett-Packard, Tennant and Friends' work, and some models produced by spreadsheet manufacturers. The hobby spreadsheet model stands out for its high engineering resources, making it resilient against damage or misuse. Although this investment might seem excessive given its use by its creator, it could be a precaution for potential future evolution into a business process-enabled use case. The spreadsheet application use case involves distributing a spreadsheet model to multiple users, possibly with modifications. This category comprises three types of models. The planned application spreadsheet model, characterized by high engineering resources and designed for distribution. The incidental application spreadsheet model, which carries risks due to medium engineering resources and lack of source code protection and input error trapping. And the quick spreadsheet model, featuring low engineering resources and intended for immediate use without any investment in readability or modifiability. The paper underscores the importance of understanding these different models to better manage spreadsheet risks and enhance their development and distribution. It stresses the need for careful planning and investment in engineering resources, depending on the intended use case and potential risks associated with each type of spreadsheet model. The concept of accidental application spreadsheet model, accidental app, emerges when a spreadsheet receives low engineering resources, posing risks of generating spurious results and maintenance difficulties. Despite these risks, such spreadsheets are often used in business settings without sufficient documentation in the literature. A new taxonomy for understanding analytical spreadsheet models has been introduced, categorizing 9 types of spreadsheets based on use cases and engineering resources. This taxonomy aims to enhance our understanding of spreadsheet development recommendations and decision-making regarding spreadsheet models. This section of the research paper focuses on the potential for further development and refinement of the proposed taxonomy. It emphasizes the need to better define engineering resource levels and use cases, as well as to systematically examine the field research on spreadsheets in light of this taxonomy. The authors suggest examining the taxonomy through lenses such as the FAST standard, practical expertise from spreadsheet manufacturers, and guidelines from organizations like ICAEW and F1F9. Moreover, the paper considers errors in analytical spreadsheet models in relation to the taxonomy, questioning whether certain types of spreadsheets are more prone or less prone to errors. It also explores the evolution and transition of spreadsheets over time, proposing 2 distinct paths. purposeful transition with careful planning and investment, and organic or accidental evolution without much forethought or investment. The authors hypothesize that a transition would typically involve moving up a row in the same column or diagonally up and to the right in Figure 7, whereas an evolution would be a move to the right of the same row, reflecting a spreadsheet being distributed more broadly without additional engineering resources. They advocate for guidelines on making smart engineering investments to facilitate purposeful transitions rather than organic evolutions, citing the importance of modifiability, transferability, and readability. Finally, they suggest generalizing insights from Olofsson and Fries, 2008, discussion on transitioning from analytical solution to industrial quality analytical spreadsheet model beyond their domain of supply chain analytical models at Hewlett-Packard. Personal productivity spreadsheets, commonly used in business settings, pose significant risks when employed as field expedient solutions. To mitigate these risks, it is essential to extend these spreadsheets to industrial quality spreadsheet models. This transition is particularly crucial when spreadsheets become embedded in routine business processes, necessitating guidance to ensure a seamless integration. Industrial quality spreadsheet models offer enhanced reliability, maintainability, and scalability, features that are critical in high-stakes business operations. The lack of guidance on this transition can lead to inadequate spreadsheet models, resulting in inaccurate data, inefficient processes, and poor decision-making. In this context, the development of a framework for extending personal productivity spreadsheets to industrial quality spreadsheet models is vital. This framework should provide a structured approach to spreadsheet development, encompassing best practices, standards, and methodologies for ensuring the quality and reliability of spreadsheet models. The authors acknowledge the valuable contributions of Professor Kourosh Dadgar and anonymous referees, whose comments and suggestions have enriched the development of this framework. The proposed framework will facilitate the transition from personal productivity spreadsheets to industrial quality spreadsheet models, thereby minimizing the risks associated with field expedient solutions and promoting more efficient and effective business operations.